359 meters above the Chenab River, a train now crosses in near silence. Below it, sheer Himalayan rock, a riverbed too far down to matter, and no ledge wide enough to stand a crane on. Nearly 30,000 tons of steel had to reach this exact point above a canyon with no road in and no way to build upward from underneath. This is the highest railway bridge on Earth. But the real problem was never the height. It was that the valley gave engineers nowhere to even begin the questions. How do you bring 30,000 tons of steel into a gorge with no usable road? Why does this crossing need an arch? And how do you build one where no ordinary crane can stand?
The gorge with no way in. First, someone had to reach the gorge at all. In the earliest years of the project, survey teams walked in. Horses and mules carried the equipment. There was no vehicle access, no staging ground, nothing beyond footpaths. So before a single piece of the bridge could arrive, engineers had to build a way in. Roughly 26 kilometers of road, carved directly into slopes that had never held a vehicle. This is young Himalayan rock, fractured, unstable, prone to collapse the moment it's disturbed. Crews stabilized what they exposed as they went, bolting and meshing the rock, because a single slide here could seal off the only route to a site hundreds of meters above a river. It took years.
Trucks could finally reach the cliff edge. But there was one problem nobody could engineer around. The roads were narrow, built for the terrain, not for convenience. Tight turns cut into a mountainside. A finished arch segment, large enough to lift into place in one piece, could never survive those turns. The gorge was finally reachable. It still could not receive a finished bridge.
The factory beside the gorge. The road solved access, but it did not mean a finished bridge could simply be driven through those mountain turns. Fabrication, therefore, became part of the site itself. Steel could reach the gorge in transportable sections. At the bridge site, fabrication facilities turned that material into larger structural components, while detailed 3D models controlled the geometry so the assemblies could meet the required tolerances before erection.
Piece by piece, something began taking shape here, on solid ground, before it ever left it. They could finally get steel to the gorge. But what kind of bridge could actually carry a railway across a span like this and survive everything this environment could throw at it?
Why the valley demanded an arch. Railway bridges generally operate under tighter limits for deflection and vibration than comparable road bridges. This bridge was designed to withstand wind speeds of up to approximately 266 kilometers per hour and engineered to resist earthquake forces corresponding to Zone 5, India's highest seismic design category. Temperatures swing sharply between Himalayan summer and winter. Add the weight and vibration of passing trains, and no single factor decided the design. The combination did.
What came out of that combination was a steel arch, a shape with exceptional stiffness for its span, where loads are carried primarily as compression through the arch ribs toward the abutments. That doesn't mean other bridge types were incapable here. Long-span suspension and cable-stayed structures cross valleys worldwide. But for this specific span, depth and seismic exposure, the arch gave engineers the predictable, low-deflection behavior this railway needed. Choosing the arch solved the railway's structural problem, but it created another one.
An arch does not simply sit on the ground. It pushes outward into whatever holds its two ends. Every ton this arch would carry needed somewhere to go, and that somewhere was the mountain itself. Investigation found rock ranging from solid to badly fractured, typical of this young, folded stretch of the Himalayas. Engineers dug deep into both slopes, grouted and reinforced the fractured sections, then anchored the abutments into rock finally capable of resisting the arch's outward force. Each side of the gorge needed its own solution. The ground could finally hold what was coming. The crane with no ground to stand on. Everything was ready, except the one thing that mattered most. 467 meters of open air stood between the two cliffs. No pier, no island, no ledge anywhere near the center to plant a crane on. How do you lift something into the middle of a canyon when there is nothing there to stand on? The answer was to make the crane itself cross the canyon.
Engineers raised two pylons on opposite rims of the gorge, the taller one climbing roughly 127 meters on the Srinagar side, and strung steel cables between them. The crossbar riding those cables could travel the full 915 meters from pylon to pylon, wider than the arch itself, carrying loads out over open air to points in the gorge where no ground existed at all. Its two lifting units were each rated at roughly 20 tons on their own hook, able to work together in tandem for lifts of up to 40 tons.
Two halves, open air. From here, the arch began to grow, not as one structure, but as two, advancing from opposite sides of the gorge at once. Each new segment swung out over the river on the crossbar, was lowered into position, then joined to the leading edge of the structure with high-strength friction grip bolts before the next piece could follow. And each growing half was not yet an arch at all. An arch only behaves like an arch once it's whole, once both ends are joined and its force has somewhere to travel. Until that moment, each advancing half is closer to an enormous diving board, a cantilever reaching further into open space with every segment added, carrying more of its own weight with less beneath it.
What held it up wasn't the bridge's future strength. It was temporary steel cables anchored back into the mountains, doing the job the finished arch hadn't earned the right to do yet. Nothing about this stage tolerated guesswork. Surveying teams tracked both advancing halves constantly, correcting for steel that could shift measurably between a cold morning and a warm afternoon. Wind speed decided when lifting could continue and when everything had to stop.
Year after year, segment by segment, the two halves crept toward the center of the gorge. By early 2021, they had closed to within meters of each other, which meant the hardest part hadn't happened yet. Two independently built cantilevers, grown from opposite mountains, now had to meet in open air across the final stretch of a 467-meter span, with only the narrowest margin for error. The day the arch became an arch, a serious mismatch at closure would have been extraordinarily difficult to correct. Every one of those years of surveying, stabilizing, and calculating led to this single moment. Engineers spent weeks fitting the last handful of segments, checking each one against its planned position before committing to the next. Nothing about that final approach allowed for improvisation. They closed the gap piece by piece until just 5.6 meters remained, a sliver against a span of nearly half a kilometer. On April 5, 2021, the final connection closed the arch. That single joint didn't just complete a shape, it changed how the entire structure behaved. Before closure, the mountainside cables had been carrying part of each half's weight. After it, engineers began releasing those cables gradually, not all at once,
as the completed arch began taking the compression it had been designed to carry and redirecting those forces into the reinforced mountains on either side. After that transfer, crews filled sections of the arch's steel box members with concrete, adding dead weight to improve overall stability. With the temporary stays removed, the completed arch could finally carry its structural load through the system it had been designed to use, holding roughly 10,000 tons of steel above the river. The gorge finally had an arch. It still did not have a railway. The railway that still had to cross. Above the arch, engineers still had to build an entire deck. Dozens of prefabricated segments, each weighing around 85 tons, and assembled on solid ground at the approaches. That created a new problem. The cable crane that had built the arch could handle up to about 40 tons in tandem, less than half the weight of one deck segment. So the method that built the arch could not simply be reused. This time, the deck would be pushed. The method is called incremental launching, a structure built in one place, then advanced forward in careful, repeated stages until it reaches its final position. Hydraulic systems push the deck out from both sides at once, a little further with every cycle, engineers monitoring alignment, gradient, and stress as steel inched over open air where nothing waited to catch a mistake. It became the first curved viaduct launch of its kind on Indian railways. Meter by meter, in careful increments, the two advancing sections crept toward each other across the top of the arch that had taken years to close beneath them. On August 13th, 2022, they met. Engineers called it the Golden Joint, the final connection completing a continuous deck from one side of the gorge to the other. It felt like an ending. It wasn't one. A deck is not yet a railway either. Track had to be laid across its full length. Connections and welds were inspected as the bridge approached its final configuration. Then came the part no design model could substitute for: putting an actual train on it. Full train trials began in June 2024. An 8-coach Mimu became the first full train to cross the Chenab Bridge, putting the completed structure under a real moving railway load. This was no longer a bridge being assembled. It was a railway being tested for operation. Even a successful trial wasn't the finish line. The testing phase could end. Monitoring could not. Continuous surveillance of wind conditions and a warning system remain part of how railway traffic is managed across the bridge. Only after all of that did passenger trains begin crossing on June 6, 2025, commissioned as part of the all-weather rail link, finally connecting the Kashmir Valley with the rest of India's network. The first service to make the crossing ran between Katra and Srinagar. It has since been extended and now runs the full corridor between Jammu Tawi and Srinagar. For a passenger, the crossing now lasts under 2 minutes. From the train, the bridge looks like a single finished object stretched across the gorge. But that is the illusion. The bridge could only exist after engineers had first transformed everything around it: the access, the mountains, even the empty space above the river, into part of the construction system. They did not begin by building the bridge. They began by making the impossible place buildable.
Yeah!